Okay, is it screen is visible to everyone? Am I audible? Yes or no? Am I audible or no? Okay, fine. Yeah, if any disturbances are there, please let me know. Yeah, let me start with some brief introduction about the dynamic programming. So it is a well-known algorithm design technique, like similar to your divide and conquer algorithms. Another strategy for designing the algorithm is dynamic programming. So it is like a divide and conquer technique. In divide and conquer technique, the problem is divided into a sub problems. Of course, there it is completely disjoint sub problems you will be getting, whereas in the dynamic, most of the problems are overlapping. So this dynamic programming is used when the problem breaks down into a recurring small sub problems. Dynamic programming is typically applied to optimization problems. In such problems, there can be a many solutions. Each solution has a value and we wish to find a solution with the optimal value. So these dynamic programming model is used to find the optimal solutions. So dynamic programming is a general algorithm design technique for solving problems identified by or formulated as a recurrence with overlapping sub instances. This is very important point. So this is overlapping sub instances mean the sub problems. Okay. So invented by American mathematician Richard Bellman in 1950 to solve the optimization problems. So the main idea here is set up a recurrence relating a solution to a larger instance to solutions of some smaller instances, solve smaller instances once, record solutions in a table and extract solution to the initial instance from the table. Dynamic programming is a way of improving on inefficiency of divide and conquer algorithm. So by inefficiency, we mean that the same recursive calls is made over and over. If some subproblem is solved several times, we can use table to store results of a subproblem the first time it is computed and thus never have to recompute it again. Okay, so in dynamic programming is applicable when the subproblems are dependent, that is when subproblem shares subproblems. So programming refers to the tabular method actually. Dynamic programming is used to solve problems with the following characteristics. Simple subproblems. We should be able to break the original problem to a smaller subproblems that have the same structure. Optimal substructures of the problems. The optimal solution to the problem contains within the optimal solutions to its subproblems. Okay, so all the optimal solutions problems contains within optimal solutions to its subproblems. Overlapping subproblems. There exist some places where we solve the same subproblems more than once. So just theory I am reading. Already the introduction part is over in the class. Okay. So the dynamic programming works on a principle of optimality. And what is this principle of optimality is? States that in an optimal sequence of decisions or choices, each subsequence must also be a optimal. Okay. So to explain that one, so I have taken the Fibonacci example, which is a recursive example. So in order to compute the current Fibonacci number, you should add the previous two numbers. So when you are calling the Fibonacci with 6, so the Fibonacci 6 is invoking the Fibonacci 5 and Fibonacci 4. So this is what a recursive. So you can look at my cursor also here. So it is a recursive, the combination of Fibonacci of n minus 1 plus Fibonacci of n minus 2. If n equal to 0 or n equals to 1, return 1. So this is what the recursive algorithm. So in this, in order to compute the Fibonacci 6, you need to know the what is the value of Fibonacci 5 and Fibonacci 6. Recursively we are calling 5 is calling 4 and 3, and 4 is calling 3 and 2. So like this, the entire tree is generated. And how the functions are called? It follows the depth first search. It starts with Fibonacci 6, 5, 4, 3, 2, 1 like this. One by one it is calling all the functions recursively to find the value of a Fibonacci 6. So these are all the function calls with the values like this. Okay, so you can see that the many times you are calling the same Fibonacci with the same value. Okay, so here you can see that the Fibonacci 4 is called 2 times, Fibonacci 3 is called 3 times. So like this you can just count and you can see how many times the same sub problem is solved repeatedly in this recursive call. Okay, so like this. But actually if you apply a dynamic model, so one time you are solving using many times. So you can see the all the blue colors are first time when you are invoking, you are finding the values, and all these green colors are whenever you are calling a Fibonacci with these values, you are not invoking the functions actually here, you are reusing the values. So whatever the Fibonacci 4 is there, you are reusing the values from this one. Okay, so which is need not call all these function calls. The green are you are just using the values, you are not calling the functions actually. Okay, so again the difference between a dynamic programming versus a divide and conquer model. So in divide and conquer model, partition of a problem into a independent smaller sub problems. Okay, so here also the partition of a problems into a overlapping sub problems. So when you divide the problem into a sub problems in divide and conquer model, the whatever the problems you solved all are disjoint sub problems. Okay, so when the problem is big, you are dividing into a smaller sub problems. In dynamic is also you are dividing, but when you are performing this division, the most of the sub problems are overlapping. Because of that, we are reducing the time complexity basically. Okay, the second point is it does not store of sub problems, because whenever you are solving the problem, because all the sub problems are disjoint sub problems, you need to solve it. That's why no need to store the values also. But whereas in the dynamic model, it stores the solutions of a sub problem, because to again once again you need not recalculate the same sub problem, you can make use of that value. So that is the intention of the second point. Okay, so it uses top down approach, whereas it uses bottom up approach. Okay, so in the divide and conquer model, you are starting with the big problem into a small sub problems like this, you are dividing and you are solving. But whereas in the dynamic model, you are not dividing the big problem into a smaller one. So you are taking the first smaller problems and you are solving, and you are combining these all the smaller problems to solve the bigger problems. Okay, again, so the difference between a dynamic programming model and a greedy model. So dynamic programming is used to obtain the optimal solution. Of course the greedy model is also used to obtain the optimal solution only. Both are used to get the optimal solutions. But in dynamic programming, we choose at each step, but the choice may depends on the solution to a sub problems. In the greedy algorithm, we make the whatever choice seems best at that moment and take and then solve the sub problems arising after the choice of its made. Okay, so whatever decision you are taking in the greedy model, it depends on your previous decision, whereas in dynamic model, it is not like that. Okay, So in direct dynamic model, it gives the guarantee of getting the optimal solution. But whereas in the greedy model, if you apply, there is no guarantee that you are going to get the optimal solution, because we are doing only the local minimum in the greedy model. Whereas in the dynamic model, the overall optimization you are doing. Examples are the knapsack problem. Fractional knapsack problem is an example of a greedy method, and 0 1 knapsack problem is for dynamic. Okay, the examples of a dynamic programming problems are 0 1 knapsack problem, trailing salesperson problem, optimal binary search tree. So today we'll discuss that one. The matrix chain multiplication, longest common sequence. Like this, there are hundreds of problems are there which comes into dynamic model. Yeah. So what is this optimal binary search tree is? First of all, a binary search tree is a binary tree. Either it is in empty or it may have the nodes. Each node in the tree contains an identifier, and all identifiers in the left subtree of tree are less than the identifier in the root node of the tree. All the identifiers in the right subtree of T are greater than the identifiers in the root node of the tree. Okay, the left and right subtrees is also a binary search trees. Okay, so the what is the definition of the binary search tree? It is a binary tree, and based on the condition you are constructing, so any element which is lesser than the root element should be there in the left subtree. Okay, and any element greater than the root element should be there in the right subtree, and it is applicable for the subtrees also, because all the subtrees also a binary search trees. Okay, so the example also you can see it here. So the root element is 55, and any element which is lesser than the root element is there in the left part, like 35 and 12, and any element which is greater than the 55 is there in the right side, that is 68, 61 and 92. Okay, so again if you take the left subtree, the left subtree contains 35 and 12, which is again left subtree of binary search tree. Left subtree is also a binary search tree with the root is 35, and the left subtree of the 35 is 12. Okay, so recursively it is applicable, the definition. It is already over in your previous one. Okay, now coming to for given data, you can construct the many binary search trees. Like if the number of elements are 3 here, the key values are 10, 20 and 30 you will be taking. And if you take the 10 as a root element, you can have a two different trees with the same root element. Whereas if the root is 20, you can see that there is a tree with the root 20. Similarly, if the 30 as a root element, so you will be getting a two different trees with the same root element. Okay, so like this there are multiple binary search trees you can construct for given element. So the basic purpose of the binary search tree is for searching the element in a database, or like there is a set of keys are there and you are going to search with a less number of comparisons. Okay, so when compared to the linear search, the binary search will take a lesser time than the linear search. Okay, so here he has given in the diagram, you can see that for searching the each element, the how many comparisons are required for each tree. Suppose I want to search a 10. If you look at the first tree, the number of comparisons which are required to search a 10 is 1, because that is the root element. Similarly, if you take a second tree, the number of comparisons is required for searching a 10 element is 1 only. Okay, but in the third tree, the number of comparisons are 2, because the 10 is not a root element here, it is there in the next level. Okay, so by looking this diagram you can understand that the how many number of comparisons are required for each key element. and if you take the average value, you can see that there is a middle tree with the root is 20 will have a less number of comparisons, that is 1.66 when compared to all other trees. Okay, so this is because all the elements will have the same probabilities. Now let us take the data in the same tree, but here the frequencies are different. The key element 10 is you are accessing 3 times, and the key element 20 you are accessing 2 times, and the key element 30 you are accessing 6 times. Okay, so 6 times the frequency is there, so you are searching for that particular element. If this is the scenario, the total number of comparisons for each tree is, for the first tree 25 comparisons are required, for second tree 21, 20, 19 and 18. The finally which is the best tree for searching is the fifth tree, which is the root is 30, the left subtree is 10, the right subtree for 10 is 20. Okay, so this is the tree which is having a less number of comparisons when compared to all other trees. Okay. So we need to find a tree, binary search tree, which gives the less number of comparisons. Okay. Whereas in the previous case, if all the elements are having the same frequency, then the middle one will be the best one. Okay. Any questions up to this you can ask now. So this part is covered in your class. Okay. Now I think this is also covered. So let us solve this binary search tree problem. So given a sequence of identifiers A1, A2, A3, A4 like this up to AN, these are all the key elements are there which are in sorted order. You can see that A1 is less than A2 and like this AN. So these are all in sorted order, the whatever key elements are there, and we want to construct the optimal binary search tree. And for every element we are assigning the frequencies, that is in terms of the probabilities. So here let P of I be an probability with which we search for A of I. What is the probability of A of I? That is a P of I value you will be getting. Okay. So similarly, it is not like that always you are searching the key elements. Sometimes you may be giving some wrong keys also which is not existed in the tree. So for that also you need to consider the what is the probability, and that is represented by using a Q of I. Okay. So let Q of I be a probability with which we search for an identifier X such that, so what will be the X value? X value is greater than A of I and less than A of I plus 1. Suppose if AI is 10 and AI plus 1 is 20, the X value is between 11 to 19. The whatever value is there, it belongs to the X. Okay. So we must build a binary search tree with a minimum expected search cost. Okay. So you can see this particular one. So there are internal nodes or the key nodes we are calling. The key nodes are 10, 20 and 30, and he has given one example. So these are all the key nodes, and the external nodes are virtual nodes which are nothing but unsuccessful search, and what is the probability of this unsuccessful search is represented by using a Q of I. So you can observe that the key elements are A1, A2, A3 is there, whereas the virtual nodes are E0, E1, E2, E3. Okay. So one extra will be there because it is from minus infinity to 9, that is E0 represents, and 11 to 19 E1 will represent. So the set of values. Similarly E2 and E3. E3 is from 31 to plus infinity. And the number of comparisons depends on the level of this particular one. Okay. Now, so when there are n elements are there, right from A1, A2, A3 up to AN, and among this all these things I can select the any element as a root element. I can select the A1 as a root element, or A2 as a root element, or A3 as a root element. Like here you can see I can select A1 is a root element 10 and A2 is a root element 20 and A3 is a root element 30. So like this it is there. Okay. So ultimately which one you have to select as a root is the root which gives the less number of comparisons. That is our intention. Okay. Suppose if I selected a root element is a of k. So what is the value of A of k? A of k value varies from 1 to n. Any value can be considered. So in general, we are writing the A of k is the root element I am taking. And if I select the A of k is a root element, the left subtree contains, what are the elements in the left subtree? The left subtree contains any element which is lesser than the root element. What are the elements which are lesser than the root element? It is from A of 1 to A of k minus 1. So these are the root elements. Okay. So similarly, what is there in the right subtree? The right subtree contains A of k plus 1 to A of n. So these are the elements in the right subtree. If I select the AK as a root element, suppose there are 4 elements are there. If I selected a A2 as a root element, so what is there in the left subtree? Only one element, that is A1. And what is there in the right subtree? A3 and A4 as a root elements. Okay. So like this, when you are selecting a one element as a root element, the left subtree contains all the lesser values right from A1 to A of k minus 1. Not only the key values, it will have the virtual nodes also. What are the virtual nodes you have? That is from Q0 to Q of k minus 1. And P1 to k minus 1. What is the P value? The probability of the key elements. What is the Q value? The probability of a virtual elements or the virtual nodes. So similarly, what is there in the right subtree? If the AK is a root element, that is P of k plus 1, means the element is A of k plus 1 to A of n. It means P of k plus 1 to P of n probabilities for key elements and Qk to Qn. These are called a virtual nodes. Okay. So you can see here the formula also, the total cost is equals to how many times you are accessing the root element, that is P of k, plus the cost of the left subtree plus cost of the right subtree plus the weight of the left subtree, because how many times you are accessing the left subtree is also important. Okay. So that is what a W of 0 comma k minus 1 will give the total frequency of the left subtree. Similarly, W of k comma n is nothing but it is the total frequency of the right subtree. So this is what the total cost of the tree. The same thing if I represented in a mathematical way, that is P of k, the probability of the kth element, plus C of 0 comma k minus 1, that is the cost of the left subtree. So when I am saying C of 0 comma k minus 1, what are the elements are there in the C of 0 comma k minus 1? It contains A1, A2 up to A of k minus 1 and Q0, Q1 up to Q of k minus 1. That is the left subtree. C of 0 comma k minus 1 means this one. Similarly, C of k comma n means what are the elements are there in C of k comma n? It contains A of k plus 1 to A of n and Q of k to Q of n. You can see here in the right part of this particular diagram. Of course, the weight of the left subtree plus weight of the right subtree. And in this formula, you can see that the weight of the left subtree contains P1 to Pk minus 1 and weight of the right subtree contains P of k plus 1 to P of n. Okay. Plus the P of k. If you add P of k with W of 0 comma k minus 1 and W of k comma n, it is nothing but it is a total weight of the tree. It is a total weight of the tree. You can say instead of writing W of 0 comma k minus 1 plus W of k comma n plus P of k, you can write down W of 0 comma n directly. So that will give the total cost of the tree. Okay. So that is what I have written here. You can see it here. C of 0 comma n is nothing but the cost of the total tree is equal to the minimum of minimum of. So minimum means, so k value is varying from 1 to n. So for every element, what is the cost that you are getting, you are computing, and among this one you need to find the minimum one. So minimum of k is varying from 1 to n. C of 0 comma k minus 1 plus C of k comma n, it is the recurrence relation to find the cost of the binary search tree, and plus w of 0 comma n will give the total weight including the root element, it will give the total weight. Okay, so that is for the whole tree. But in general, how do you represent that one? C of I comma j is equal to the minimum of k is varying from I plus 1 to j, and C of I comma k minus 1 plus C of k comma j, and W of I comma j. So this is the formula is there to find the cost of the any subtree. Okay, the C of 0 comma n is the main tree, and this is in general we are giving. Okay, so let us take the problem. Before going to the problem, so if you have any questions you can ask now. Yeah, any questions? Yeah. Okay, let n equals to 4. I think today I given the same problem. If 1 minute. Let us take n equals to 4, that is the number of elements in the binary search tree. So a1, a2, a3, a4 as a key elements, and the values are given as a do, if, in, while, which are in sorted order according to the dictionary. Okay, for our convenience, so we'll be taking 10, 20, 30, and 40. So what is the probability of each element is, so p of 1 to 4, because there are 4 key elements are there, 3 comma 3 comma 1 comma 1, these are the frequencies of the key elements. So similarly, you may be searching for the elements which are not there in the tree, and what are the probabilities is q of 0 to 4. So q0 is 2 value, it means you are accessing the elements from minus infinity to less than a1 or less than 2. Okay, so these are the frequencies of unsuccessful search. Okay, so according to the formula, that is C of 0 comma 4, C of 0 comma 4 is nothing but the total cost of the binary search tree is equals to, so there are 4 possible trees are there with 4 different root nodes. If I select the a1 as a root element, I am getting this kind of expression, that is, if I select the A1 as a root element, the left subtree doesn't have any elements, but right subtree contains A2, A3 and A4. Because C of 1 comma 4 will have A2, A3, A4 and Q1, Q2, Q3 and Q4. If I select the A2 as a root element, then you can see the second expression. The left subtree contains only one element, that is A1, and the right subtree contains two elements, that is A3 and A4. This is the expression you are getting if I select the A2 as a root element. Similarly, if I select the A3 as a root element, I am getting like this, C of 0 comma 2. It means if I take the A3 as a root element, left subtree contains A1 and A2 and right subtree contains A4. That is what you got it, the expression. So similarly in the fourth one, if I select the A4 as a root element, then the left subtree contains A1, A2, A3, and the right subtree contains empty tree because there is no elements is there in the right part. Okay, so this is what the expression you will be getting. So in order to solve the C of 0 comma 4, first you should know the what is the cost of C of 0 0 and C of 1 comma 1. Similarly, C of 0 1, C of 2 comma 4, like this. You should know all the subtree values, subtree cost. Okay, then only you are able to find the C of 0 value. So in the dynamic model, what exactly we are doing is we are not going in a top down approach. So we are coming from bottom to top. It means first you are solving the small subtrees problems, then you are solving the main problem. Okay, so in the process of solving the problem, let us look at the subtree which doesn't have any nodes. So how many empty trees are there actually? If you look at a tree, how many empty trees are there? Like if you look at in the previous diagram, yeah, look at. So how many empty trees are there in this one? E0 is a one empty tree, E1 is another empty tree, E2 is another empty tree. Like this, these are all empty trees. Why I am saying it is a empty trees? Because it doesn't have any key elements. Okay. So first you are finding the what is the cost of the empty trees. What is the cost of the empty trees actually? What is the cost of the empty tree? Zero, because there is no elements are there. How many comparisons you are doing? Zero comparisons are you are doing. That's why all C of 1 comma 1 is 0. The cost of the empty tree is 0. That is what you are written. So C of 0 comma 0, 1 comma 1, 2 comma 2, all these are empty trees. Why it is empty trees? It doesn't have any element. Only one node is there. That is called a virtual node. Okay. And what is W of I comma I? What is the weight of the empty tree? Even though it is empty tree, we are accessing many times. So that Q will give the frequency of the empty tree. That's why W of I comma I is Q of I and C of I comma I is 0 and R of I comma I. What is the root element in the empty tree? Null only. That's why it is written 0. So C of I comma is a cost of the subtree and C of R of I comma is a root of the subtree and W of I comma is the weight frequency of the subtree. Okay. So you can see this formula W of I comma J is equals to P of J plus Q of J plus W of I comma J minus 1. So this is the formula you remember. It is a recursive one. Is it this point is clear for everyone? That is empty tree will have a frequency but cost is 0 only because empty tree doesn't have any key element. There is no comparison. Okay, that's why it is defined like that. Now I want to construct the tree which contains exactly one node. I want to construct the binary search tree which contains exactly one node. So what are the possible one node subtrees you will be getting? That is, you may have A1, you may have A2 or A3 or A4. So like this, you will be having a single node subtrees. Okay. So you can see this one in the next diagram. I am showing you pictorially. So first we are computing the what is the frequency of W of 0 comma 1. First of all, you should know what is there in the W of 0 comma 1. In 0 comma 1, you have a E0, you have a E1. Because W of 0 comma 1 means what are the virtual nodes are there? Q0, Q1. That is what E0 and E1. And what are the key element is there? The key element is A1. Is it point is clear for everyone? If you have doubts, you can rise now. Because in W of 0 comma 1, it is a small tree which contains only single key element. And what is the key element is A1 here. Okay. So pictorially you can see the tree here. Now what is the cost of this particular tree? W of 0 comma 1 is equal to P of 1 plus Q of 1 plus W of 0 and 0. So what is the value of W of 0 and 0? You can see it here in the previous one. W of 0 and 0 is nothing but Q of I. So what is Q of I? Q of 0. Q of 0 is 2 value. So 2 plus Q of 1 is 3. P of 1 is 3. 3 plus 3 is 6. 6 plus 2. Total 8. So what is W of 0 comma 1? It is a frequency of that particular tree. So that is the weight you are saying. It is a 8. Now what is the cost of this particular tree? C of 0 comma 1 is equals to, so W of 0 comma 1, the weight of the tree plus minimum of, if I select the A2, A1 as a root element, because C of 0 comma 1 will have only one element A1. And if I select the A1 as a root element, the left subtree doesn't have any elements, right subtree doesn't have any element. That's why these two are empty subtrees. Okay. So the minimum of C of 0 comma 0 plus C of 1 comma 1. C of 0 comma 0 is E naught. That is 0. Number of comparisons are 0. C of 1 comma 1, 0. So 0 plus 0 will give 0 value. Okay. 0 plus W of 0 comma 1 value, 8. So 8. So what is the root element you are selected in the R of 0 comma 1? You are selected the A1 as a root element. So pictorially this is the tree. In mathematics, by using the formula, by using a recurrence relation, we find that the cost of the single node is 8. If you manually also you can verify it. Let us verify manually. So A1, what is the probability of A1? 3 times. How many comparisons are required to access the A1? One comparison. So it means the total number of comparisons for A1 is 3 only. 3 plus. Okay. So how many times you are accessing E0? 2 times. How many comparisons are required to tell that that element is not there? Only one comparison, because only one element is there. So that's why this is 2. So 3 plus 2 plus E1. What is the probability of E1? 3. So if you add up all these three values, you are getting the 8. So what is the cost of the tree which contains only one A1 element? Is a 8. Okay. So similarly, so now there is a subtree which contains only one node, but this time the single node is A2. It is not the A1. If single node is A2, how do you represent that one? W of 1 comma 2. The W of 1 comma 2 contains only the element A2, and the left subtree contains E1 virtual node, and the right subtree contains E2 virtual node. Okay. So these two are there in the left subtree and right subtree. So what is the weight of W of 1 comma 1? The weight of W comma 1 comma 1 is probability of second element plus probability of unsuccessful search for E2 plus W of 1 comma 1. The total value is 7. So W of 1 comma 1 is nothing but Q of 1, that is 3, plus Q2, that is 1, and 3. So if you add up, you will be getting a 7. Now what is the cost of this particular tree? C of 1 comma 2 is equals to W of 1 comma 2, how many times you are accessing this subtree, plus the minimum of C of 1 comma 1 plus C of 2 comma 2. Why you are getting C of 1 comma 1, C of 2 comma 2? Because you are selected the A2 as a root element in the C of 1 comma 2 subtree. When you select the A2 as a root element, the left subtree will have only E1 and the right subtree will have only E2. And what will be the cost of this particular single node tree is 7. So that is the cost of this one. If you do it manually also, you will be getting the same. Now which is the root element in this one? R of 1 comma 2. It is not 0 comma 1. It is R of 1 comma 2. It is wrong, this one. So R of 1 comma 2 will give the root element is 2. 2 means the key element number. So similarly, there is one more subtree you may get it with a single node. What is the node here? It is A3 node. So what is the cost of 2 comma 3? It is 3 only. So because you are accessing only three comparisons you are doing for all these operations. Okay, so this is for a single node. So similarly, you'll be getting one more subtree which contains only one node, and this time the root node is a4. Okay, so this is the smaller subtrees. So the smaller subtrees I'm constructing. Initially we started with empty trees. Now exactly one node. Now the next time you are going a subtrees which contains exactly two nodes. So what are the possible trees you will be getting? Is you may have a A1 and A2, or A2 and A3, or A3 and A4 you will be getting. Okay. Let us take the first case. So W of 0 comma 2. So what is there in the W of 0 comma 2? It contains E0, E1, E2 and A1 and A2 as a key element. So W of 0 comma 2 is equals to P of 2 plus Q of 2 plus W of 0 comma 1. So W of 0 comma 1 value already you computed previously. You can check out if you want. W of 0 comma 1 already we computed with 8 value. Okay. Now 3 plus 1 plus 8 will give the 12 value. So what is the cost of this particular one? C of 0 comma 2 is equal to the minimum of these two trees, because with the two elements how many trees you will be getting? You will be getting a two different trees. That is, I can select the A1 as a root element. If I select the A1 as a root element, the left subtree contains only E0 and the right subtree contains A2. Not only A2, E1 and E2. You can see in the first expression, if I select the A1 as a root element, so you will be getting this one, C of 0 comma 0. That is a cost of the left subtree which contains only E0 plus C of 1 comma 2. Similarly, if I select the A2 as a root element, I am getting the second expression. That is C of 0 comma 1 plus C of 2 comma 2. Okay. So that is A2, if I select the root element, the left subtree contains A1 along with A1. E0 and E1 is there. But whereas in the right side, only empty tree with E2. Okay. So now among these two possible trees of given C of 0 comma 2, whichever value is a minimum value, that you are considering as a subtree, because you need to find out the sub solutions of a suboptimal only. Okay. So here minimum is equal to 0 comma 0 plus 7, that is for first tree, 8 plus 0 for second one. Among the 7 and 8, which is the minimum one? 7 is the minimum value. So it means which tree is a optimal tree among these two combinations? The first tree will be the optimal one. So that's why you will be taking a 7 plus 12 will give the 19. So what is the cost of the tree? Is 19. Because of which node as a root node? Because of A1 as a root node. Okay. So the first tree is an optimal tree when compared to the second one. So that is how you got it from the mathematical one. So R of 0 comma 2 is equal to 1, which is nothing but A1 as a root element. Any questions for this one? You can ask now. So now I am trying to construct the tree which contains the exactly two nodes. So what are the two nodes here? A1 and A2 as a two nodes. So now which is the optimal binary search tree among these two nodes is the first one. Okay. Now coming to this next tree. So what is the next subtree? The tree which contains exactly two nodes, but this time the nodes are A2 and A3, not A1 and A2. Okay. So among this A2 and A3, that is what W of 1 comma 3. W of 1 comma 3 is equal to P of 3 plus Q of 3 plus W of 1 comma 2. It is a direct mathematical formula and you will be getting a 9 value. And C of 1 comma 3 is equals to the minimum of these two. So the first tree, that is C of 1 comma 1 plus C of 2 comma 3, and the second tree is C of 1 comma 2 plus C of 3 comma 3. So the first tree, if you select the A2 as a root element, the left subtree is a empty tree, that is C of 1 comma 1, and the right subtree will have one key element and two virtual nodes, or two virtual nodes. Okay, that is what the C of 2 comma 3. Okay, so among these two trees, you got a 0 plus 3 here, 7 plus 0, and 3 comma 7. Among this 3 comma 7, which is the minimum value? 3 value. So 3 value you are getting because of which tree? Because of the first tree. So which is the root element you are selecting now? The A2 as a root element, and which is the subtree which is considering for a optimal solution? This one, not this one. This is very expensive. Okay, so similarly I am constructing one more tree exactly contains a two element, that is A3 and A4. Okay, so what is the cost of A3 and A4? Here also you are getting 0 plus 3, 3 plus 0. So anyone you can select it. Among these two, anyone is a root element, you can select it, because the total cost of the tree is same in this case. Okay, so I selected again the first one as a root element. So R of 2 comma 4 will give the 3. 3 means the root element number. Okay, so now you constructed the tree which contains exactly two nodes, the values you computed. Again, now you need to construct the tree which contains exactly three nodes. Okay, so among these three nodes, I can select the A1 as a root element, or A2 as a root element, or A3 as a root element. If I select the A1 as a root element, the right subtree contains A2 and A3. So it is again directly a formula. C of 0 comma 3 is equal to minimum of, if I select the A1 as a root element, I am getting C of 0 comma 0 plus C of 1 comma 3. That is the first tree. If I select the A2 as a root element, I am getting C of 0 comma 1 and C of 2 comma 3. Okay, so similarly, if I select the A3 as a root element, I am getting C of 0 comma 2 plus C of 3 comma 3. Okay, so among this one, that is 0 plus 12 and 8 plus 3, 19 plus 0. So among these three, which is minimum one? 11 will be the minimum value. So how you are getting 11? If I am selecting the A2 as a root element, and the left subtree contains A1 with E0 E1, and the right subtree contains A3 with E2 and E3. Okay, so this is the tree which contains exactly three nodes, and the three nodes are A1, A2 and A3. And which is the optimal one among these three trees? The middle one will be the optimal one. That's why the root element that you are selected for these three is 2. That is R of 2 comma 4 will give the, not R of 2 comma 4, this is R of 0 comma 3. So that is wrong. Okay, so that is what we selected. Now one more possible tree you are getting, a tree which contains exactly three nodes, but this time the elements are A2, A3 and A4. Previously it is A1, A2, A3, but this time it is A2, A3 and A4. So there are three elements are there. If I select the A2 as a root element, I am getting the first expression. If I select the A3 as a root element, I am getting the second one. And if I select the A4 as a root element, I am getting the last one, this one. Okay, so among this, if I select 8, 10, 12, so which is the minimum value? 8. So how you are getting the 8 value? Because of the first tree, that if I select the A2 as a root element, I am getting that particular tree. Okay, so that's why I selected the sub tree. I am selecting only suboptimal tree. I am not looking the second and third one, which is not a optimal subtrees. Among these three, this is the optimal subtree. You know that optimal solution will also have the suboptimal solutions. That's why I am ignoring the other things. Now finally, so you are going to construct the tree which contains exactly 4 nodes. What are the 4 nodes are there? A1, A2, A3, A4. So if I select the A1 as a root element, I am getting this expression, that is C of 0, 0 plus C of 1 comma 4. If I select the A2 as a root element, I am getting this expression. If I select the A3 as a root element, I am getting this one. Like this, A4, I am getting this one. Plus W of 0 comma 4, the total weight. So minimum of C of 0, 0 is 0 plus 19, 8 plus 8, 19 plus 3, 25 plus 0. So among this, which is the minimum value here? The 16 is the minimum value. So 16 plus 16, the total value you are getting is 32. Okay. So how you are getting 16 actually here? Because of the second value. What is the second value? This one. So C of 0 comma 1 plus C of 2 comma 4. So it means if I select the A2 element as a root element, I am getting the optimal solution, that is a 32. Okay, so this is the complete table is there. So initially you computed W of 0, 0 value and W of 1, 1, W of 2, 2, W of 3, 3, W of 4, 4. Similarly C of 0, 0, cost of the empty trees all are zeros here. Then you constructed a tree which contains exactly single node. So what are the single node? A1, A2, A3, A4. Now you have constructed a tree with exactly two nodes, that is C of 0 comma 2, 1 comma 3 and 2 comma 4. Now you computed exactly three nodes, that is 0 comma 3 and 1 comma 4. Now finally you constructed the whole tree, that is 0 4, which contains exactly 4 nodes. Okay, so you can easily write an algorithm for this particular one by using iterative statement. So here you are just make use of previous values to compute the new values. Okay, so this is the OBST one. Any questions from your side you can ask.